All right, now we want to look at triple integrals in spherical coordinates. In x, y, and z coordinates, triple integrals look like this. When we convert them to spherical coordinates, there's three things we have to do. We've got to convert the function. That's probably the easiest part, because for every x, you just replace it with rho sine phi cos theta, and y gets replaced with rho sine phi sine theta, and z is rho, what is it, rho cosine phi. The limits of integration are going to be depending on how we do the integral out here. The question is, the big question, or at least our first question is, what does the dv turn into? Okay, so let's take a look at that, and then we'll come back and look at these things depending on what the region E is. So dv, here we go. All right, so what I have here are two spheres. Now you can't see both of them because one of them is inside of the other. One is radius 2, one is radius a little bit more than 2. What do I have? 2.1. Okay. What I want to do though is I want to look at a little bit of volume. That is, I want to start at a particular point. I'm going to change my theta by a little bit. I'm going to change my phi by a little bit, and I'm going to change r by a little bit, and it's going to create a little bit of volume. Okay, so essentially what I'm saying is I'm going to be starting at 2 and changing r by 0.1, or rho by 0.1. So radius changes by 0.1. Now let's take a look at this. In the blue one, I want to say let's start my theta at 1 radian, and let's go to say 1.5 radians. Okay, so there's a wedge there that's from 1 to 1.5 radians. Phi is still going from 0 to pi. So let's do this here. Let's let phi go from 1 to 1.5 as well. What's that? 1. Oops, I'm on the wrong surface. Sorry. I'll get there. Whoa. There we go. Sorry. Phi is going from 1 to 1.5. Okay, so what we see here is that little patch of the plane corresponding to this point right here, where phi and theta are both 1. So you change theta by a half a radian, you change phi by a half a radian, and it describes that little patch of the sphere. Okay, I want to do the same thing underneath here on the smaller sphere. So this is going from 1 to 1.5, and likewise here from 1 to 1.5. Right? So it's kind of hard to see the difference between those two. So let's actually make this a little bit bigger here. Let's change this by 1.3 maybe. All right. So I've changed my theta by a half a radian, changed my phi by a half a radian, and I've changed rho by 0.3. Okay, so the smaller sphere gets blown out into the bigger sphere. Now, if I were to connect the corresponding corners here, connect those two corners, connect these two corners, connect these two corners, and the ones in the back, I'd have a little bit of volume. And the question is, how much volume is there? Well, one thing to notice is that this depends on several things. I mean, keeping the same change in theta and change in phi, if I go, instead of from 2 to 2.3, let's say, I go from 1 to 1.3, that's a smaller volume than I had before. Likewise, if I were to move further out, 3 to 3.3, whoa, what just happened? Let's try that again. 3 to 3.3, there we go. That's actually going to be bigger volume. So this volume element is going to depend on rho, on the radius, but it also depends on some other things. it turns out, maybe you convince yourself of this, that it doesn't really depend on theta. For instance, if I'm going theta from 1 to 1.5 or 2 to 2.5, right, by just sliding that around over to there, it's not changing the amount of area that's there, and if the thickness isn't changing, it's not changing the volume. So that's not really, it doesn't really depend on theta. However, I think you can see that it will depend on phi. So if I go from, let's say, 0.1 to 0.6, so still the same change of a half a radian, you can see that this right here is a very different area than what I had down here, and so when I give that little bit of thickness to it, it's going to have a different volume than that one did over there. So it seems to me that the volume element is going to depend both on rho and on phi, but not theta. Okay, so let's actually go and calculate what it is. Okay, so hopefully the picture that you just saw is going to get you through my drawing here, because my drawing is never as good as that. So I'm starting off at a point out here in space. I've got some fixed phi already, some value of rho, and some value of theta here. And what I'm going to do is I'm going to change theta by a little bit, right, which would rotate this around to here. I'm going to change phi by a little bit, which rotates it down to there. And I'm going to change rho by a little bit, which kind of pushes everything out. Right? And I'm looking for the volume of that little thing. Well, it's very cubical, and it's not unreasonable to assume that I can just do length times width times height. Well, I can see that in one direction here, this radial direction, that's just a small change in rho. Right? Going this way, that comes from changing the phi, and it's an arc length. It's an arc length with radius rho, right? So this thing right here should be rho times the change in phi. Okay. And now I want to look at this way. Well, that way again is a little bit of arc length, but that little bit of arc length now, the change in the angle is d theta, but what's the radius, right? Well, the radius we get from drop, because theta turns this way, so it's like around the z-axis. So if I drop a perpendicular right from there, I guess I already have that perpendicular dropped right from there. So I guess I didn't draw this in the right place. Let's get rid of that. And so that arc is really down here. Yeah, so drop that straight down. There's that. So this arc, which is going to be that arc, or maybe this one up here, is whatever this length is times that change in theta, right? So that angle there is d theta. What's this right here? Well, this is the radius, which is the same as that, which is rho times the sine of phi. So this is rho sine phi. So this arc length right here is that radius times that angle, rho sine phi times d theta. And so that little bit of volume now is the length times the width times the height. It's rho sine phi d theta, that's this one, times rho d phi times d rho, for a grand total of rho squared sine phi times d rho d theta d phi d phi d theta d rho, whichever order you choose to put them in, whichever is most convenient for you. In polar coordinates and cylindrical coordinates, we had this factor of r in there. Well, in spherical coordinates, it's a little more complicated. It depends both on r and on phi. Okay. So anyway, that's dV that you have to plug in to here, right? That's what's going to go there. I'm going to do an example in the next video.